Question, it says, draw the orbital energy diagram, hint, for the following species, copper atom. You may use a noble gas core. Please make sure to get the energy order correct for the 3D and 4s sublevels. Which is higher energy? All right, now is the time that we get to talk about this. And we will. Let's start like we do the last problem, and so many of these problems, this homework and this lecture outline. So you have a copper atom. You have to write the electron configuration for that copper atom. To do that, you need to go to your periodic table and see that copper has 29 electrons for an atom. Now, using a noble gas core for this, you notice that the first 18 electrons are for the same for argon. Then you're going to go 4s2, 3d, almost all the way across to 9. And I'm not done yet, but following the shape of the periodic table, my answer will be argon, 4s2, 3d9. But that is not correct. And argon is an exception to the follow the shape of the periodic table rule. So I'm going to write exception. And does anybody remember how the electron configuration changes because it is an exception from the lecture outlines? Well, so it's now that I'll point out there are 5 exceptions that you have to know. Copper is one of them. And what happens is, go ahead.
Now, I just found it. Basically, the 3D fills first and then the 4S.
That's right. So the answer is not 4s1 3d9, or sorry, 4s2 3d9, it's 4s1 3d10. Okay? Yeah, thank you, Selden.
And is that only for, and that's for the coinage metals, correct? The copper, the silver, and the gold, and that's it?
Okay, so those are 3 of the 5 exceptions you have to know. So I'll list them right here. Copper, silver, and gold. And then there are 2 other exceptions that you have to know. Those are chromium and molybdenum. And I'll cover all of them as we go through this, but let's start with copper. Well, and let me just tell you that chromium and molybdenum, I'll give you the example for chromium, but chromium and molybdenum are right underneath of each other on the periodic table. So we're not surprised that they have similar properties, similar chemical properties. Chromium is going to be argon, 4s1, 3d5. And we end up filling the 3D completely for the coinage metals, or the Ds. There'll be 3D, 4D, and 5D, as we'll see. Completely, and so they borrow 1 electron from 4s to do it. Chromium borrows 1 electron from 4s to be half filled. And as far as we can get into it, is that half filled and fully filled D sublevels are slightly more stable, slightly lower in energy, and that's why this happens. And so 2 things to remember. First off, memorize that it does happen. Second off, it is because half-filled and fully filled D sublevels are slightly lower in energy than otherwise. Okay. Anyway, so those are the 5 exceptions that you have to know. And it turns out that if you look at your periodic table, that down to gold, those are most of the exceptions. As you get farther and farther down the periodic table, you will run into more and more exceptions, because the atoms just get that much more complicated. However, we don't have to know any of the other exceptions. If you wanted to know the electron configuration of element 109 meitnerium, named after the famous woman scientist Lisa Meitner, who discovered at least a couple elements, what you would do is you could assume that it follows the shape of the periodic table, and then if you really needed to know, you just go look it up, right? So all of this information is available. So we do want you to know that there are some exceptions. We do want you to understand why these exceptions exist, as far as because the full and half full D sublevels are slightly lower in energy. And now let's do a full-blown discussion of 3D versus 4S and which is lower in energy. And then we'll come back and we'll answer this question. So 3D versus 4S. The examples that I'm going to do, and these should be from the lecture outlines, but I think it's a really good time to review them. If we look at the potassium and the calcium ion, or atoms, what we see, and I'll choose the calcium atom because I think I did potassium in the lecture outline. The calcium atom's electron configuration with a noble gas core is argon 4s2, which means that for the calcium atom, and this is also true for the potassium atom and all the atoms before that, by the way, but for the calcium atom, there are 2 electrons in the n equals 4 level, or well, there are 2 electrons in the 4s sublevel, but no electrons in the 3D sublevel. And hopefully that's a statement that everybody can agree with. If not, I'm happy to say more about it. Now, the next statement, however, is that electrons always go to the lowest energy place. Electrons always go to the lowest energy place. If the electrons are in the 4s sublevel and not in the 3D sublevel, that means that the 4s sublevel is lower in energy. So electrons always go to the lowest energy place. If there are electrons in 4s but none in 3D, 4s must be lower in energy. Than 3D for the calcium atom. Okay? Now, again, we're on a little journey here. The story is not complete. If you'll allow me to tell you a little bit more of the story. So let's draw the calcium, or let's draw an atom. And I'm going to draw, well, I'll draw 4s. And then I'll draw inside of it the n equals 3 level. And really, when we draw the n equals 3 level, it's 3s that we're drawing because 3p and 3d fit inside of it. Now, when you do a 3D sublevel, there are already electrons in the 3s and the 3p sublevels. And in fact, we know that 3p, one of them goes right here, and one of them goes right here, and the other one comes out of the page, and I won't draw that. But what you can see is with the 3s and the 3p, let's call it 3px and 3py, that there already are some electrons in the 3s and the 3p sublevels. And so what happens is that 4s, even though it is larger, to put electrons in the 3D, the electrons would experience electron-electron repulsions. So to finish this statement, there are already electrons in the 3s and 3p sublevels, so the 3D electrons experience electron-electron repulsions. So even though 4s is larger, which tends to be higher energy, 3D can be higher energy due to these electron-electron repulsions. Okay? Well, I'm out of paper here, so I'm going to have to go over on the back. Now let's talk about the scandium atom. Scandium, one of the lesser known elements, it's only element 21 though. Scandium atom has 21 electrons, and it has a noble gas core for argon, then 4s2 3d1. But then we make the scandium Sc plus ion. And what is observed is that the electron configuration is argon. Well, I'm going to make the scandium plus 2. That means it's lost 2 electrons. And when it does that, it loses the 4s2 electrons and is left with 3d1. This is what is observed. And just like we previously said that electrons go to the lowest energy place first, so higher energy electrons leave the atom first. So the 4s electrons must be higher in energy than the 3d electrons. Than the 3d1 electron. So now 4s for scandium, 4s is higher energy than 3d. For scandium. And this is a very long way of going, but basically right here on the periodic table is where the switch occurs. For potassium, calcium, and smaller atoms, 4s is lower in energy than 3d. For scandium and all atoms after that, 3d is lower in energy than 4s. And that's what's observed. Now, let's come back to our picture of the atom. When we move from calcium to scandium, what happens to the number of protons? Can anybody tell me? Calcium to scandium.
It increases.
The number of protons increases. Thank you. And when the number of protons increases, the 3D sublevel and all of the n equals 3 sublevel shrinks because it's pulled closer to the nucleus. And that's what makes 3D become lower in energy, is the 4s stays the same size, but 3D shrinks as you go from calcium to scandium. So 3D shrinks for scandium, and that's why it's lower in energy. And I'm happy to say more about it, but here's the level of understanding that we need to start with. Before, so calcium or before, 4s is lower in energy. Scandium and after, 3D is lower in energy. And that's going to affect our answer for this problem. Okay. Anyway, now I can actually get back to the problem. The problem said, if you'll remember, I know it was a long time ago, draw an orbital energy diagram for a copper atom using a noble gas core. Here's what that looks like. Orbital energy diagrams always look like an energy arrow on the left. And by the way, we've drawn last homework energy arrows for ladder diagrams as well. So there is a common theme here with energy. We have the first 18 electrons for argon. Then for the copper atom, there's 4s1 and 3d10. And what I'm saying is for sorry for shuffling the paper so much, but copper is after scandium. Copper has 3d lower in energy than 4s. 3d holds 10 electrons, so that means it has 5 orbitals, and all of them are filled. Nope, that's bad form. I should do one in each. And then you put 4s1. So this is a proper orbital energy diagram for the copper atom. And it must have 3d lower in energy than 4s. Any questions about that? It was a long road to get here, but we've finally done
Yes,
it.
Professor, I have a question.
Dimith, go ahead.
And how did we apply the exception here?
How did I apply what?
The exception for copper.
Ah, the exception for copper. Okay. So let's go back. And so there are 29 electrons. And following the shape of the periodic table, we would have guessed that the answer was argon 4s2 3d9. But according to the fact that copper is an exception, we change one of the electrons so that it's 3d10, and then that electron makes it 4s1. So this is the exception part.
Oh, okay. And
Okay.
also, if we had another atom after scandium, we should just have changed the position of the 3D and 4s.
Okay. Good question. For scandium and anything, so anything in this row, anything all the way down in the periodic table, 3D is lower in energy than 4s. So it doesn't matter which one you do from now on, 3D is lower energy than 4s. And then at calcium and before, 3D is higher in energy than 4s. So 4s would be lower.
Okay, thank you.
Sure. Any other questions? Okay. Oop. I think we can stop going on.